John Bardine's place in history as the only physicist to win the Nobel Prize in Physics twice is not just a fact to be memorized, but a story that unfolds across decades of scientific change, quiet determination, and intellectual depth. His achievement stands alone, not because others lacked brilliance, but because the circumstances, mindset, and nature of his work aligned in a way that rarely happens in science. To understand why this matters, it is important to step into the world of 20th century physics, a time when the foundations of modern technology were still being laid and when unanswered questions about matter and energy challenged even the greatest minds. The Nobel Prize in Physics is awarded for discoveries that fundamentally change how humans understand or use the laws of nature. Winning it once places a scientist among the elite. Winning it twice in the same field suggests something even more extraordinary: the ability to revolutionize physics not just in one area, but in two entirely different domains. John Bardeen achieved this rare distinction by contributing to two of the most important developments of modern science: the invention of the transistor and the explanation of superconductivity. These achievements were not incremental improvements. They were turning points that reshaped both theory and application. What makes Bardeen's double Nobel especially remarkable is that his two prizes were separated by 16 years and addressed problems that, on the surface, seemed unrelated. The first dealt with solid-state electronics, the behavior of electrons in semiconductors, and the practical challenge of amplifying electrical signals. The second addressed a deep theoretical mystery that had puzzled physicists for decades: how certain materials could conduct electricity with zero resistance. Few scientists possess the breadth of knowledge and adaptability required to master such distinct challenges, yet Bardeen moved between them with calm precision. Bardeen's journey did not begin with dramatic declarations of genius. Born in 1908, he grew up in an environment that valued education and careful thinking. From an early age, he displayed a strong aptitude for mathematics and problem-solving, but he was never drawn to fame or competition. This quiet temperament would later define his scientific career. Unlike many celebrated physicists who thrived on debate and public recognition, Bardeen preferred working behind the scenes, focusing on ideas rather than attention. The first Nobel Prize he received, in 1956, recognized work that would eventually touch nearly every human life. The transistor emerged at a time when electronics were limited by the size and fragility of vacuum tubes. Engineers and physicists knew that progress depended on finding a smaller, more reliable way to control electrical currents. At Bell Laboratories, a hub of innovation, Bardeen joined a team tasked with solving this problem. His role was deeply theoretical. He sought to understand how electrons behaved at the surfaces of semiconducting materials, a question that seemed abstract but proved essential. Bardeen's insight into surface states allowed the team to overcome a major obstacle that had stalled earlier attempts at building a solid-state amplifier. Without this understanding, the transistor might have remained an unrealized concept for years. When the first working transistor was demonstrated, it marked the beginning of a technological revolution. Radios became portable, computers became feasible, and the path toward integrated circuits and modern digital devices was opened. For this contribution, Bardeen shared the Nobel Prize with his colleagues, but even among them, his theoretical clarity stood out. For many scientists, such an achievement would represent the culmination of a lifetime. The Nobel Prize often serves as a symbolic finish line. Yet for Bardeen, it marked a transition rather than an ending. After leaving Bell Laboratories, he moved into academia, where he turned his attention to a problem that had long resisted explanation. Superconductivity had been discovered in 1911, but despite decades of research, no one could fully explain why certain materials suddenly lost all electrical resistance at low temperatures. The phenomenon seemed to defy conventional understanding. What followed was one of the most profound intellectual efforts in modern physics. Bardeen, working with Leon Cooper and John Robert Schrieffer, developed what became known as the BCS theory. This theory proposed that electrons in a superconductor could form pairs, now called Cooper pairs, allowing them to move through a material without resistance. The idea challenged traditional assumptions about electron behavior, yet it matched experimental evidence with striking accuracy. The development of the BCS theory was not a sudden flash of inspiration. It was the result of years of careful reasoning, mathematical rigor, and collaboration. Bardeen's role was central, guiding the theoretical framework and ensuring its consistency with known physical laws. When the theory was finally published, it provided a unified explanation for superconductivity and opened new avenues of research in condensed matter physics. In 1972, this work earned Bardeen his second Nobel Prize in Physics, making him the first and only person to achieve this honor. The significance of this achievement extends beyond personal recognition. Bardeen's 2 Nobel Prizes symbolize the power of theoretical understanding to drive practical change. The transistor transformed technology, while the theory of superconductivity reshaped physics itself and enabled advances in medical imaging, particle accelerators, and energy research. Together, these contributions illustrate how deep knowledge of fundamental principles can lead to breakthroughs that alter society. Equally important is the manner in which Bardeen achieved this distinction. He was not a charismatic showman or a dominant personality. Colleagues often described him as modest, patient, and generous with credit. He valued collaboration over competition and believed that the best ideas often emerged from collective effort. This attitude allowed him to work effectively with others and to remain open to new perspectives, even late in his career. Bardeen's story also challenges common assumptions about genius. His success did not come from dramatic risk-taking or relentless self-promotion. Instead, it came from persistence, clarity of thought, and a willingness to tackle difficult problems without concern for recognition. He pursued questions because they mattered, not because they promised rewards. This mindset allowed him to continue producing groundbreaking work long after achieving fame. Being the only physicist to win 2 Nobel Prizes is not merely a statistical anomaly. It reflects a rare combination of qualities: intellectual depth, versatility, humility, and endurance. Bardeen's achievements remind us that science advances not only through bold personalities, but also through quiet thinkers who patiently uncover the underlying structure of reality. In the broader history of science, John Bardeen stands as a figure who bridged theory and application, individual insight and teamwork, ambition and humility. His dual Nobel Prizes are a testament to what is possible when curiosity is paired with discipline, and when a scientist remains committed to understanding the world at its most fundamental level. His legacy continues to shape the technologies we rely on and the scientific questions we continue to explore. The transformation of electronics and modern technology through John Bardeen's work is a story that unfolds quietly but powerfully across the 20th century. It is not a tale of sudden spectacle, but of gradual change that reshaped the foundations of how humans communicate, compute, store information, and interact with the world. Before his contributions, technology was constrained by physical limits that seemed unavoidable. After his work, those limits began to dissolve, opening a future that few could have imagined. In the early decades of the 20th century, electronic devices depended almost entirely on vacuum tubes. These glass components could amplify electrical signals, making radio, early television, and primitive computers possible. Yet they were large, fragile, energy-hungry, and unreliable. Machines built with vacuum tubes overheated easily, failed often, and occupied entire rooms. Engineers knew that progress required something smaller and more stable, but no one had a clear path forward. The behavior of electrons inside solid materials was still poorly understood, and without that understanding, innovation stalled. This was the technological environment John Bardeen entered. His impact did not begin with a new gadget or a dramatic invention, but with a deeper understanding of how matter behaves at the smallest scales. Bardeen focused on the physics of solids, particularly semiconductors, materials that conduct electricity under certain conditions but resist it under others. At the time, semiconductors were known, but their potential was largely unrealized because their behavior seemed unpredictable and difficult to control. Bardeen's contribution was rooted in theory. He investigated how electrons behave at the surfaces of materials, especially at the boundary between different substances. These surface effects turned out to be critical. Earlier attempts to build solid-state amplifiers had failed because electrons at the surface interfered with the flow of current in unexpected ways. Many researchers treated these effects as minor complications. Bardeen recognized them as the central problem. By developing a clear theoretical explanation of surface states, Bardeen helped remove a major barrier to progress. This understanding allowed for the successful creation of the transistor, a small device capable of controlling and amplifying electrical signals without the need for vacuum tubes. Though the transistor itself was physically small, its implications were enormous. It represented a complete shift in how electronic systems could be designed. Once transistors replaced vacuum tubes, electronics began to shrink. Devices became more reliable, consumed less power, and could operate for longer periods without failure. Radios became portable. Computers, once massive machines used only by governments and large institutions, began a slow but steady process of miniaturization. The transformation was not immediate, but it was unstoppable. Each improvement built upon the transistor's fundamental advantages. The transistor did more than replace an older component. It changed the logic of design itself. Engineers could now imagine systems composed of thousands, then millions, of tiny electronic switches working together. This possibility led directly to integrated circuits, where multiple transistors could be placed on a single piece of semiconductor material. Integrated circuits made complex electronics affordable and widely accessible. Without them, modern computing would not exist. As these technologies matured, their influence spread far beyond laboratories and factories. Communication systems were transformed. Telephone networks became more efficient and reliable. Satellite communications became feasible. Later, digital signals replaced analog ones, enabling clearer transmission of voice, data, and images. Each of these advances traced its lineage back to the transistor and the scientific understanding that made it possible. Bardeen's work also influenced how scientists and engineers approached innovation. His success demonstrated that breakthroughs often come from solving fundamental problems rather than chasing immediate applications. By focusing on why electrons behaved the way they did, rather than simply trying to force a device to work. He set a model for research that combined theory with practical relevance. This approach became a guiding principle in modern technology development. The transformation extended into computing in profound ways. Early computers relied on thousands of vacuum tubes and were prone to constant failure. With transistors, computers became smaller, faster, and more dependable. Over time, this led to personal computers, laptops, and eventually smartphones. These devices are now so integrated into daily life that it is difficult to imagine a world without them. Yet their existence depends on the principles Bardeen helped uncover. Modern technology also benefited from Bardeen's later work on superconductivity, even though it belonged to a different phase of his career. Superconductivity enabled technologies that require extremely efficient electrical transmission and powerful magnetic fields. Medical imaging devices such as MRI machines rely on superconducting magnets. Particle accelerators, used to explore the fundamental nature of matter, depend on superconductivity to function effectively. These applications extend the reach of electronics into medicine, research, and energy. The broader impact of Bardeen's work lies in how it altered society's relationship with technology. Electronics became personal rather than institutional. Information became mobile rather than fixed. The speed at which data could be processed and shared increased dramatically. These changes reshaped economies, education, and culture. While Bardeen did not design smartphones or the Internet, his contributions made them possible at the most basic level. What is striking about this transformation is how invisible its origins often seem. Most users of modern technology are unaware of the scientific principles that enable their devices. The transistor operates silently, billions of times per second, without drawing attention to itself. This invisibility mirrors Bardeen's own personality. He was not a public figure who sought recognition. His influence spread quietly, embedded in the fabric of everyday life. Bardeen's role in transforming technology also highlights the importance of collaboration. Although he made critical theoretical contributions, the practical realization of his ideas depended on teamwork. Scientists, engineers, and technicians worked together to refine and apply the transistor. This collaborative model became standard in modern research and development, where complex technologies require diverse expertise. The transformation of electronics did not stop with hardware. Software, digital logic, and information theory all flourished because the underlying physical components became reliable and scalable. Without transistors, software as we know it would be impractical. The digital age rests on the assumption that electronic components can switch states quickly and accurately, an assumption made valid by Bardeen's work. As technology advanced, it also changed how science itself is conducted. Powerful computers enabled simulations, data analysis, and modeling that were previously impossible. Scientific instruments became more precise and automated. In this way, Bardeen's contributions created a feedback loop. Better technology enabled better science, which in turn led to further technological progress. The transformation he helped initiate continues today. Advances in artificial intelligence, renewable energy systems, and quantum computing all depend on principles rooted in solid-state physics. Even as new materials and techniques emerge, the intellectual foundation remains connected to the insights Bardeen provided decades earlier. In reflecting on how his work transformed electronics and modern technology, it becomes clear that the impact is not confined to a single invention or era. It is woven into the structure of contemporary life. From communication and health care to education and entertainment, the effects are everywhere. Bardine's legacy is not defined by fame or visibility, but by the enduring presence of technologies that have become essential to modern existence. This transformation illustrates how deeply theoretical understanding can shape the practical world. By explaining how electrons behave in solids and how they can move without resistance, Bardeen helped unlock possibilities that extend far beyond physics. His work stands as a reminder that the most profound technological changes often begin with quiet questions about how nature works, asked by individuals willing to pursue understanding for its own sake. The story of John Bardeen's key role in inventing the transistor is not a dramatic tale of a single moment of discovery, but a slow, careful unfolding of ideas, experiments, and persistence. It takes place in a period when science and technology were standing at a crossroads, searching for a way forward beyond the limitations of existing tools. To understand Bardeen's role, it is necessary to step into that moment in history and see how deeply his thinking shaped one of the most important inventions of all time. In the early 1940s, the world was becoming increasingly dependent on electronic systems. Radios, radar, and early computing devices were vital, especially during wartime. Yet all of these technologies relied on vacuum tubes, which were bulky, fragile, inefficient, and prone to failure. Engineers knew that these limitations were holding back progress, but no clear alternative existed. The idea of controlling electrical current inside a solid material had been discussed for years, but every attempt to make it work ended in frustration. This challenge drew together a group of scientists at Bell Laboratories, one of the most advanced research centers of the time. Among them was John Bardeen, a physicist with a deep understanding of quantum mechanics and solid-state physics. Unlike some of his colleagues, Bardeen was not focused on building devices through trial and error. He wanted to understand the fundamental behavior of electrons inside materials, believing that real progress could only come from theory grounded in physical reality. At the heart of the problem was the mysterious behavior of semiconductors. These materials did not behave like good conductors such as metals, nor like insulators such as rubber or glass. Their ability to conduct electricity depended on impurities, temperature, and electric fields. While this made them difficult to control, it also hinted at great potential. If their behavior could be understood and manipulated, they might replace vacuum tubes entirely. Early attempts to create a solid-state amplifier failed repeatedly. Electrical signals behaved unpredictably, refusing to amplify as expected. Many researchers assumed the problem lay deep inside the material, in the bulk behavior of electrons. Bardeen approached the problem differently. He suspected that the surface of the semiconductor played a far more important role than anyone realized. At the boundary between the semiconductor and its environment, electrons behaved in ways that interfered with the intended flow of current. Bardeen's insight into surface states proved to be decisive. He realized that electrons trapped at the surface created electric fields that blocked the movement of other electrons. This effect prevented earlier devices from functioning properly. By identifying this issue, Bardeen did something crucial. He transformed a vague engineering problem into a clearly defined physical one. Once the cause was understood, it became possible to design around it. Working closely with experimental physicist Walter Brattain, Bardeen tested these ideas in the laboratory. Their collaboration was marked by constant exchange between theory and experiment. Bardeen provided explanations and predictions, while Brattain refined experimental techniques to test them. This partnership led to the creation of the first working point, contact transistor, in 1947. Though crude by modern standards, it demonstrated that electrical signals could indeed be amplified within a solid material. The transistor was small, required little power, and generated minimal heat. More importantly, it worked. This success confirmed Bardine's belief that understanding the physics of materials was the key to technological progress. The device was soon improved and refined, leading to more stable and scalable designs. The fundamental principle, however, remained rooted in Bardine's theoretical work on electron behavior. Bardine's role in the invention of the transistor was not limited to solving one specific problem. His broader contribution was helping to establish solid-state physics as a serious and productive field. Before the transistor, much of physics focused on particles, radiation, and atomic structure. The success of semiconductor research showed that studying the collective behavior of electrons in solids could lead to powerful applications. This shift reshaped both physics and engineering. The impact of the transistor spread rapidly. Initially used in specialized applications, it soon found its way into consumer electronics. Radios became portable and affordable. Military and industrial systems became more reliable. Over time, the transistor replaced vacuum tubes almost entirely. Each new application reinforced the importance of the original breakthrough. What is often overlooked is how fragile this moment of discovery was. Without Bardine's insight into surface states, the project might have failed or been abandoned. His contribution did not involve dramatic experiments or bold public claims. It involved careful reasoning, attention to detail, and the willingness to challenge assumptions that others took for granted. This quiet intellectual courage was essential to the transistor's success. The invention of the transistor also revealed something important about the nature of innovation. It showed that transformative technologies often emerge from collaboration rather than individual brilliance alone. Bardine's theoretical work complemented Brataine's experimental skill and William Shockley's broader vision. Each played a role, but Bardine's understanding of the underlying physics was the glue that held the effort together. Despite the magnitude of the achievement, Bardine remained characteristically modest. He did not seek public recognition or leadership positions that would draw attention to himself. Even after the transistor began to change the world, he continued to focus on research and teaching. This humility shaped how he approached science throughout his career. The transistor's influence extended far beyond what anyone at the time could have predicted. It enabled the development of integrated circuits, which combined multiple transistors onto a single chip. This, in turn, led to microprocessors, memory devices, and modern computing. The exponential growth in computing power that defines the digital age can be traced back to the principles established during those early experiments at Bell Laboratories. Every modern electronic device depends on the transistor. Smartphones, laptops, medical equipment, satellites, and data centers all rely on billions of transistors working together. Though these devices are vastly more complex than the original point, contact transistor, they operate on the same fundamental ideas. The physics Bardine helped uncover remains relevant, even as materials and manufacturing techniques evolve. The invention of the transistor also changed how science and industry interacted. It demonstrated that fundamental research could lead directly to practical applications with enormous economic and social impact. This realization influenced how governments, universities, and corporations invested in research. The model of long-term theory data-driven investigation became more widely accepted as a path to innovation. Bardine's role in this transformation highlights the power of asking the right questions. Instead of asking how to force a device to work, he asked why it failed. This shift in perspective made all the difference. By identifying the true source of the problem, he enabled a solution that others had missed. The transistor did more than improve technology. It reshaped human life. Communication became faster and more accessible. Information could be stored, processed, and transmitted on an unprecedented scale. Entire industries emerged around electronics and computing. These changes influenced education, healthcare, entertainment, and global connectivity. Yet through all of this, Bardeen remained focused on understanding rather than outcome. He viewed the transistor not as an end, but as evidence that the laws of physics, when properly understood, could unlock remarkable possibilities. This attitude allowed him to move on to new challenges later in his career, including the theory of superconductivity. Looking back, it becomes clear that Bardeen's key role in inventing the transistor was not defined by a single act, but by a way of thinking. His ability to see beneath the surface of a problem, to connect abstract theory with practical reality, and to work patiently with others made the transistor possible. The device itself may be small, but the ideas behind it were vast. The legacy of the transistor continues to grow as technology advances. New materials, such as silicon alternatives and nanoscale structures, build upon the same foundational principles. Each new generation of electronics carries forward the intellectual heritage of those early discoveries. In the end, Bardeen's contribution to the invention of the transistor stands as a powerful example of how quiet insight can lead to world-changing results. It reminds us that behind every piece of modern technology lies a story of careful thought, collaboration, and persistence. Through his role in creating the transistor, John Bardeen helped open the door to the modern world, shaping the way humanity lives, works, and connects. John Bardeen's later work on explaining superconductivity represents one of the most profound intellectual achievements in modern physics. By the time he turned his attention fully to this problem, he was already internationally known for his role in inventing the transistor. Yet superconductivity was a very different kind of challenge. It was not about building a device or improving technology directly, but about solving a mystery that had resisted explanation for more than half a century. What Bardeen accomplished in this phase of his career was not simply an extension of his earlier success, but a demonstration of how deep theoretical insight can illuminate one of nature's most puzzling phenomena. Superconductivity had been discovered in 1911 when scientists observed that certain materials, when cooled to extremely low temperatures, suddenly lost all electrical resistance. Electric current could flow through them indefinitely without losing energy. This behavior seemed almost magical. According to classical physics, resistance was unavoidable. Electrons moving through a material were expected to collide with atoms and lose energy as heat. Yet superconductors defied this expectation completely. For decades, physicists could describe what happened, but not why it happened. As experimental techniques improved, more superconducting materials were discovered, and their behavior was studied in great detail. Scientists measured critical temperatures, magnetic effects, and other properties, building a large body of data. Despite this, a fundamental explanation remained elusive. Many theories were proposed, but none could account for all the observed facts. Superconductivity became one of the great unsolved problems of physics, a reminder that even well-established laws had limits. When Bardeen entered this field, he brought with him a distinctive way of thinking. He believed that even the most mysterious phenomena must ultimately be consistent with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. Rather than searching for exotic new forces or principles, he focused on understanding how known interactions might combine in unexpected ways. This approach required patience, mathematical rigor, and a willingness to question assumptions that had guided earlier research. Bardeen did not work alone. He collaborated closely with two younger physicists, Leon Cooper and John Robert Schrieffer. Each brought a different strength to the effort. Cooper contributed key insights into how electrons might interact in a solid, while Schrieffer developed powerful mathematical tools to describe complex quantum systems. Bardeen played a central role in shaping the overall theory, ensuring that it remained grounded in physical reality and consistent with experimental evidence. The key breakthrough came from a radical but elegant idea. In ordinary conditions, electrons repel each other because they carry the same electric charge. This repulsion was long thought to make superconductivity difficult to explain. Bardeen and his colleagues realized that under certain conditions, electrons could instead form pairs. These pairs, later called Cooper pairs, behaved very differently from individual electrons. By pairing up, electrons could move through a material in a coordinated way that avoided the usual sources of resistance. This pairing mechanism was subtle. It did not rely on direct attraction between electrons, but on their interaction with the vibrations of the crystal lattice in a solid. As electrons moved through the lattice, they distorted it slightly, creating a kind of indirect attraction that allowed pairs to form. This idea transformed the understanding of superconductivity. It showed that resistance, free current, was not a violation of physical laws, but a natural consequence of quantum behavior under the right conditions. The theory that emerged from this work, known as the BCS theory, provided a complete and consistent explanation of superconductivity in many materials. It explained why superconductivity only occurred below certain temperatures, why magnetic fields could destroy it, and how energy gaps formed in the electronic structure of superconductors. Most importantly, its predictions matched experimental results with remarkable accuracy. For the first time, superconductivity was no longer a mystery, but a phenomenon that could be understood and calculated. Bardeen's role in developing this theory was crucial. He ensured that the theory connected abstract mathematics with measurable physical quantities. His experience in solid-state physics allowed him to bridge the gap between theory and experiment. Colleagues often noted his ability to see the essential features of a problem without becoming lost in technical details. This clarity was vital in a field as complex as superconductivity. The impact of the BCS theory extended far beyond its immediate success. It reshaped condensed matter physics, providing a model for how collective behavior could emerge from simple interactions. The idea that particles could act together in coherent ways became central to many areas of physics, including superfluidity and later developments in quantum materials. In this sense, Bardeen's work influenced not just one phenomenon, but an entire way of thinking about matter. In 1972, Bardeen, Cooper, and Schrieffer were awarded the Nobel Prize in Physics for their explanation of superconductivity. For Bardeen, this was his second Nobel Prize in the same field, a distinction no other physicist has achieved. The award recognized not only the importance of the theory, but the extraordinary nature of his career. He had contributed decisively to both the technological revolution of electronics and the theoretical foundations of modern physics. What makes this achievement even more striking is Bardeen's personal approach to science during this period. He was known for his modesty and lack of ego. Even as his work gained recognition, he remained focused on teaching, mentoring students, and continuing research. He did not seek to dominate discussions or impose his views. Instead, he listened carefully, encouraged collaboration, and allowed ideas to develop naturally. The explanation of superconductivity also had significant practical consequences. Although Bardeen himself was primarily motivated by understanding, the theory eventually enabled new technologies. Superconducting magnets became essential in medical imaging, particularly in MRI machines. Particle accelerators used superconductors to achieve higher energies more efficiently. Research into energy transmission and quantum computing continues to build on the principles established by the BCS theory. At a deeper level, Bardeen's work on superconductivity demonstrated the power of quantum mechanics to explain complex, real-world phenomena. It showed that even macroscopic effects, visible on human scales, could arise from the collective behavior of particles governed by quantum laws. This realization strengthened confidence in the theoretical framework of physics and inspired further exploration into the quantum nature of matter. The journey toward explaining superconductivity was not easy or straightforward. It involved years of failed attempts, competing theories, and intense debate within the scientific community. Bardeen's contribution lay not just in the final result, but in his persistence and intellectual discipline. He was willing to revisit assumptions, refine ideas, and work through difficult mathematics until a coherent picture emerged. His success in this area also highlights an important aspect of scientific progress. Breakthroughs often come when experience from one field is applied to another. Bardeen's background in solid-state physics and his understanding of electron behavior in materials were essential in solving the superconductivity problem. This cross-pollination of ideas allowed him to see connections that others had missed. Through his explanation of superconductivity, Bardeen reinforced a central lesson of science, that nature's most surprising behaviors often have elegant underlying explanations. What once seemed inexplicable became understandable through careful thought and collaboration. This transformation from mystery to knowledge is at the heart of scientific inquiry. In reflecting on this phase of Bardeen's career, it becomes clear that his contribution to superconductivity was not an isolated success, but part of a larger pattern. He consistently focused on fundamental questions, trusted theoretical reasoning, and worked patiently with others. These qualities allowed him to achieve something unparalleled in physics. The explanation of superconductivity stands as a testament to Bardeen's intellectual depth and versatility. It complements his earlier technological achievements and completes the picture of a scientist who shaped both how we understand the world and how we live in it. Through this work, John Bardeen left a legacy that continues to influence physics, technology, and the pursuit of knowledge itself. John Bardeen's success was shaped not only by his intelligence, but by the way he approached science, people, and problems. His career offers a powerful example of how collaboration, curiosity, and deep theoretical thinking can work together to produce extraordinary results. Unlike the popular image of the lone genius making dramatic discoveries in isolation, Bardeen's achievements grew out of steady inquiry, shared effort, and a lifelong commitment to understanding rather than recognition. From the beginning of his career, Bardeen demonstrated an intense curiosity about how the physical world works. He was not satisfied with surface explanations or approximate answers. When confronted with a problem, he wanted to understand its underlying principles. This curiosity was not driven by ambition or competition, but by genuine interest. Colleagues often remarked that Bardeen seemed motivated simply by the desire to know why things behaved the way they did. This mindset allowed him to persist through difficulties that might have discouraged others. Curiosity alone, however, was not enough. Bardeen combined it with deep theoretical thinking. He had a rare ability to move comfortably within the abstract world of mathematics and quantum mechanics, while remaining closely connected to physical reality. His theoretical work was never detached from experiment. Instead, it served as a guide, helping to identify what questions to ask and what phenomena mattered most. This balance between abstraction and practicality became one of his greatest strengths. When working on the transistor at Bell Laboratories, Bardeen's theoretical insight helped transform confusion into clarity. Many researchers were experimenting with semiconductors, but progress was slow because the behavior of electrons seemed unpredictable. Bardeen's curiosity led him to question assumptions that others accepted, particularly regarding the role of surface effects. His theoretical analysis revealed that these effects were central to the problem, not secondary. This realization redirected the entire research effort and made success possible. Collaboration played a crucial role in turning theory into reality. Bardeen did not attempt to work alone or claim ownership of ideas. He collaborated closely with experimental physicist Walter Brattain, whose laboratory skills complemented Bardeen's theoretical strengths. Their partnership was built on mutual respect and open communication. Ideas flowed back and forth, with theory guiding experiments and experimental results refining theory. This collaborative process was essential to the invention of the transistor. Bardeen's approach to collaboration was marked by humility. He listened carefully to others and welcomed criticism. Rather than dominating discussions, he allowed ideas to develop collectively. This attitude created an environment in which creativity could flourish. Colleagues felt comfortable sharing incomplete thoughts and unconventional ideas, knowing they would be considered seriously. Such an atmosphere is often where breakthroughs emerge. The same pattern appeared later in Bardeen's work on superconductivity. Faced with one of the most difficult problems in physics, he again turned to collaboration. Working with Leon Cooper and John Robert Schrieffer, he helped build a theory that none of them could have developed alone. Each brought a different perspective, and Bardeen's role was to integrate these perspectives into a coherent whole. His deep theoretical understanding ensured that the emerging theory remained consistent with known physical laws. Curiosity also drove Bardeen to remain open to new ideas, even when they challenged established views. The concept of electrons forming pairs in a superconductor was unconventional and counterintuitive. Yet Bardeen recognized its potential and helped develop it into a rigorous theory. His willingness to explore such ideas reflected a mindset that valued understanding over tradition. He did not reject ideas because they seemed strange, nor did he accept them without careful analysis. Deep theoretical thinking gave Bardeen the tools to evaluate ideas objectively. He could distinguish between speculation and insight, between mathematical elegance and physical relevance. This ability was especially important in superconductivity research, where many competing theories existed. Bardeen's discipline allowed him to focus on approaches that could be tested and refined, ultimately leading to a theory that matched experimental results. Bardeen's collaborative nature extended beyond formal research partnerships. As a teacher and mentor, he encouraged students to think independently and ask fundamental questions. He did not impose his own views or demand conformity. Instead, he guided students toward developing their own understanding. Many of his students went on to make significant contributions to physics, carrying forward his approach to inquiry and cooperation. Another key aspect of Bardeen's success was his patience. He did not expect immediate results or quick recognition. Both the transistor and the theory of superconductivity required years of effort and repeated setbacks. Bardeen's curiosity kept him engaged during these periods of uncertainty, while his theoretical discipline provided a sense of direction. He trusted that careful work would eventually lead to progress. This patience was closely tied to his humility. Bardeen did not view science as a competition to be won, but as a collective effort to expand knowledge. He was willing to share credit and acknowledge the contributions of others. This attitude strengthened his collaborations and enhanced the quality of his work. It also set him apart in a field where ego can sometimes overshadow substance. The combination of curiosity, collaboration, and theory also influenced how Bardeen navigated his career. After achieving immense success with the transistor, he did not attempt to capitalize on his fame or remain in the same area for comfort. Instead, his curiosity led him to a new and challenging problem in superconductivity. This decision required confidence in his abilities and a willingness to start fresh in a field with many unknowns. Bardeen's theoretical strength allowed him to make this transition successfully. He could apply fundamental principles across different areas of physics, adapting his knowledge to new contexts. This flexibility is rare and reflects a deep understanding that goes beyond technical expertise. It enabled him to contribute meaningfully to two distinct revolutions in science. The collaborative environments Bardeen fostered also had long-lasting effects on scientific culture. His work demonstrated that major breakthroughs often emerge from teamwork, rather than individual brilliance alone. This lesson influenced how research groups were organized and how interdisciplinary collaboration was valued. In modern science, where problems are increasingly complex, this model has become essential. Bardeen's success also shows that curiosity-driven research can have profound practical consequences, even when applications are not the primary goal. His work on semiconductors and superconductivity was motivated by understanding, yet it led to technologies that transformed society. This outcome challenges the idea that research must be narrowly targeted to be useful. Instead, it suggests that investing in deep theoretical exploration can yield unexpected benefits. Throughout his life, Bardeen remained focused on the joy of discovery. Even after receiving 2 Nobel Prizes, he continued to work, think, and teach with the same quiet dedication. He did not see his achievements as endpoints, but as part of an ongoing process of learning. This perspective kept his curiosity alive and his contributions relevant. The documentary style arc of Bardeen's career reveals a consistent pattern. Faced with complex problems, he sought to understand their foundations. He worked with others who complemented his strengths. He applied rigorous theory to guide exploration, and he remained patient and humble throughout the process. These qualities, combined, explain how he achieved what no other physicist has. In the end, Bardeen's story offers a broader lesson about success in science and beyond. It suggests that true innovation arises not from ego or haste, but from curiosity that never fades, collaboration that respects diverse perspectives, and thinking that reaches deeply into first principles. His life shows that when these elements come together, they can change not only a field of study, but the world itself.